Episode 13 solved one problem. Different writers can safely change different parts of the same Kubernetes object, but it ended with a timing question. Here in this case, the user has already scaled the checkout app deployment from 3 replicas to 5, while the deployment controller is still finishing work that began when the desired count was 3. If status is updated now, how can we tell whether it describes the latest desired state or the older one? The status value by itself does not answer that question. We can see that 5 replicas are desired and only 3 are available. That could mean the new request is failing, or it could simply mean the controller has not finished processing the 5 replica request yet. We first need a way to identify which version of the desired state the controller is talking about. Kubernetes gives us the first part of the answer through metadata.generation. Think of generation as a number for a particular version of the desired state. Kubernetes maintains this number. The client does not choose it. When we read checkout app, generation helps us identify which desired state version is currently stored. On a real cluster, you can read the deployment generation directly with kubectl. A simple analogy is a kitchen receiving revised instructions. Version 7 says, prepare 3 meals. A moment later, version 8 says, prepare 5 meals. The kitchen may still be finishing version 7 when version 8 arrives. The version number does not tell us whether the cooking succeeded. It simply tells us which instruction is newer. Generation plays a similar role for Kubernetes' desired state. Now apply that idea to our checkout app deployment. At generation 7, it asks for 3 replicas. The user scales the deployment to 5 replicas. That changes the desired state, so Kubernetes advances the deployment generation from 7 to 8. Generation 8 now identifies the newer desired state of 5 replicas. You can also connect the change to the number itself, scale the deployment, then read its new generation. After the scale request, the desired deployment says 5 replicas. While the rollout continues, the controller may update status from 3 available replicas to 4. That changes the stored deployment object, but it does not create a new desired state. So the resource version can change while generation stays at 8. This is why generation is different from resource version. Resource version helps identify the stored version of the object and can change whenever anything about the object is updated. Generation focuses on the desired state version. So a status write can produce a new resource version while generation stays the same. Resource version asks, which stored object version is this? Generation asks, which desired state is this? To see the difference in practice, print generation and resource version side by side. Now return to our timing problem and put the events in order. Checkout app starts at generation 7 with 3 desired replicas. The controller begins processing generation 7. Before that check finishes, the user changes the desired count to 5, so generation becomes 8. A moment later, the older reconciliation finishes. We need status to tell us that this result belongs to generation 7. This is where ObservedGeneration helps. The deployment controller records which generation it has observed in status.ObservedGeneration. Here the deployment has already moved to generation 8, but the status still reflects generation 7. So ObservedGeneration is 7, which tells us the controller has not caught up with the latest desired state yet. Now we can quickly tell whether the status is up to date. The deployment is already at generation 8, but the controller is still reporting status for generation 7. That simply means the controller is one step behind. It does not necessarily mean something is wrong. The controller may just still be processing the latest change. For troubleshooting, this one command is especially useful because it puts the desired generation, observed generation, and rollout counters next to each other. A useful way to think about this is a document review. The latest document is revision 8, but the review on your desk was written for revision 7. That review may be completely correct for revision 7 and still be outdated for the document you have now. ObservedGeneration gives Kubernetes readers the same kind of context. Next, the controller receives another chance to reconcile checkout app. This time it reads generation 8 and sees that 5 replicas are desired. It checks the current cluster state, takes whatever action is still needed, and writes a new status based on generation 8. Now ObservedGeneration can move to 8. But matching generation numbers do not mean everything is working perfectly. They only tell us that the deployment controller has seen the latest desired state. It may reach all 5 replicas successfully, or it may discover that something is preventing new pods from being created. In both cases, ObservedGeneration can still be 8. So ObservedGeneration tells us the status is current, but not whether the rollout succeeded. So we need one more piece of information. ObservedGeneration tells us that the deployment controller has seen the latest desired state, but it does not tell us what happened during the rollout. For a deployment, that detail comes from conditions such as available, progressing, and replica failure. Each one describes a different part of the deployment's current state. A deployment condition can be viewed as a set of status cards comprising of type, status, reason, and message. And the type tells you what each card is about or what Kubernetes is describing, for example, progressing or available. Status gives the answer as true, false, or unknown. Reason gives a short explanation, while message gives more detail for people. Deployment conditions also record when the condition was updated and when its true, false, or unknown state last changed. To inspect the deployment conditions directly, you can print each type together with its status and reason. The words true, false, and unknown only make sense together with the condition type. Progressing equals true is a statement about rollout progress. Available equals false is a statement about minimum availability. And unknown means Kubernetes cannot currently determine that particular answer. So we should always read the type and status together. Now return to generation 8. The deployment controller has already seen the latest generation, so ObservedGeneration is also 8. But only 3 of the 5 requested replicas are available, and suppose this deployment needs at least 4 to meet minimum availability. The status is current, while the rollout is still moving toward the desired result. There is an important detail about deployment conditions. Progressing equals true does not always mean the rollout is still unfinished. While Kubernetes is updating the replica set, the reason may say replica set updated. After the rollout completes, progressing can still remain true, but the reason changes to new replica set available. That is why the reason matters as much as the true or false value. A little later, all 5 replicas are available. Generation and ObservedGeneration are still 8 because the desired state has not changed again. Available becomes true, and progressing remains true with the reason new replica set available. Now the status is both current and describing a completed rollout. When you mainly want to know whether the deployment rollout has finished, kubectl has a command built for exactly that. Current status can also describe a failure. Suppose the user scales the deployment to 6 replicas, creating generation 9. The controller sees generation 9, but a quota prevents Kubernetes from creating the 6th pod. ObservedGeneration can still be 9 because the controller has seen the request, while replica failure becomes true with a reason such as failed create. If the rollout stops making progress for longer than the deployment's progress deadline, Kubernetes can report that directly. ObservedGeneration may still match generation because the controller has seen the latest request, but the progressing condition becomes false with the reason progress deadline exceeded. So again, freshness and success are 2 separate questions. Now imagine the user changes the deployment again, so generation becomes 10. But status.observedGeneration is still 9, and the last available condition still says true. If we look only at available equals true, we may assume the latest change is already healthy. But generation 10 with observed generation 9 tells us that the whole deployment status is still from the previous desired state. There is one API detail worth knowing. A deployment condition does not carry its own observed generation field. For a deployment, we judge freshness from the top-level status.observedGeneration. Some other Kubernetes APIs use the standard metav one condition shape, which can include observed generation on each condition. So the exact status fields depend on the resource we are reading. When you are unsure which fields a deployment condition actually exposes, ask the API schema instead of guessing. Deployment conditions also have two useful timestamps. Last update time tells us when that condition was most recently updated. Last transition time tells us when its status last changed, for example, from progressing true to progressing false. So last transition time is not a heartbeat that should move on every controller check. You can also print the two condition timestamps directly when reconstructing when a rollout state changed. The reason and message fields turn a condition into something we can actually troubleshoot. Progressing equals false tells us the rollout is not making progress. The reason progress deadline exceeded gives automation a short explanation, and the message can give a person more detail about what happened. For the human-readable explanation, print the condition type together with its reason and message. For a deployment, we can now read status in 3 simple steps. First, compare generation with observed generation to see whether the controller has seen the latest desired state. Second, look at replica counts such as updated, ready, available, and unavailable replicas. Third, read the conditions, especially their type, status, reason, and message, to understand what the rollout is doing and why. This gives us 4 common situations. Observed generation behind generation means the controller is still catching up. Matching generations with progressing true and reason replica set updated means the latest rollout is being processed. Matching generations with available true and a progressing reason of new replica set available means the rollout has completed successfully. And matching generations with replica failure true or progressing false means the latest desired state was seen, but the rollout has a problem. Now replay the original timing race using our checkout app deployment. It starts at generation 11 with 3 replicas. The user scales it to 5, so generation becomes 12, while observed generation is still 11. For that short period, the old status belongs to the previous desired state. Then the deployment controller sees generation 12, updates observed generation to 12, and conditions show whether the rollout is progressing, complete, or failing. In production, this gives us a practical debugging checklist. First, compare metadata generation with status observed generation. Then check updated, ready, available, and unavailable replicas. After that, inspect available, progressing, and replica failure conditions, especially their reason and message. Finally, correlate those fields with events and deployment controller activity when you need the full timeline. And when you are debugging an unfamiliar rollout, kubectl describe is a good broad starting point because it brings the deployment details, conditions, and related events together. The complete model is now simple. Generation tells us which desired state of the deployment is current. Observed generation tells us which generation the deployment controller has seen. Replica counts show how far the rollout has moved, and conditions explain what is happening and why. So before trusting a deployment status, first check whether it has caught up, and then interpret what the rollout is telling you. Now suppose the user deletes the checkout app deployment itself. That deployment has replica sets, and those replica sets have pods. How does Kubernetes know that these dependent objects can be cleaned up when their owner disappears? And more generally, what if an object must wait for some cleanup to finish before Kubernetes is allowed to remove it completely? In the next episode, we will follow that deletion path. We will see how owner references connect owners to dependents, how garbage collection removes Kubernetes dependents, and how finalizers can hold deletion open until required cleanup has finished.